I'll try to make the sample also exactly as 20 questions. And we will have the sample exam on 15th. Is that okay? April 15th. And the real exam will be on April 22nd. We'll give 1 week time because, like when you go through the sample, then you will find out, well, I need to do a little bit more reading or more practice. So I'd like to give you 1 week time between the sample and the real exam. So just to make it clear, on 15th, we will have the sample exam. On 20th, if there are any questions, you can send me an email on the sample exam and I'll be able to answer individual questions rather than wasting all your time. And 22nd, which is Thursday, we will have the real exam. And May 4th, I believe, is the final exam, right? Is that what you have in your calendars? Can somebody check, please? Does anyone take notes on when the finals are?
I have it as May 4th.
May 4th? Okay. So May 4th will be the final. So between the second exam and the final, I believe we'll have 2, 3 meetings in which we will talk a little bit about magnetism and superconductivity. So these are two important topics of inorganic chemistry, which will be part of the final exam on May 4th. Is that clear to all of you folks?
Yeah, I just have a quick question.
Sure.
So for the final exam, that will be online as well. We don't come in.
No, no. This course, it's all completely online. There are no in-person instruction for this class.
Okay, thank you.
You really look at the final exam schedule, for this course, they will not give you the place or the venue for exam. When you don't have the room number assigned for a final exam, it tells you it is an offline exam. Am I clear here, folks? And how is the video today? Is that better than before, or is it still?
Yes, it's way better.
It's a little better?
Way better.
Way better. Oh, great. Excellent. So you can see me and you can see the board and everything. Nice. Okay. So today we will get into the frost diagrams. I'm going to share my screen here, and I just want to make sure that you all can see it because we'll go through a couple of transparencies here just to show you how frost diagrams work. It's an extension of a Latimer diagram, but it is done differently. As you know, the Latimer diagrams are line diagrams. On the other hand, the frost diagrams are graphical representation of the redox potentials. So we'll try to see how to construct a frost diagram, and I'll tell you what we can learn from a frost diagram. How do we read a frost diagram? What kind of information the frost diagram will tell us, okay? So that's the topic. So between now and the lectures, if you have any questions, please feel free to interrupt me. Can you all see my graph here?
I can see it.
Now, can you see my share screen? Okay, good. So a frost diagram is a graphical illustration that tells you about the relative stability of different oxidation states relative to its elemental form. So for example, if I have nitrogen, right? Nitrogen can be NH4 plus. What is the oxidation state of nitrogen in ammonium ion? Can anyone quickly calculate and tell me what it is? NH4 plus ammonium ion. Is it about -3? Yeah. How about NH2OH? What's the oxidation state of nitrogen there? -1? Is that what you get? All right. So if you go to nitrogen gas, N2 gas, what is the oxidation state there? Elements in their uncombined state have an oxidation state of, we all know this, right? 0. So if you look at HNO2, Nitrous acid. What's the oxidation state of nitrogen there? +3. And if you go to HNO3, it's +5. So nitrogen can exist in multiple oxidation states. The point here is, what is the relative stability of all these different oxidation states relative to its elemental form? That is the gas itself. So how is that different? So that's what we're going to do. So the way we do this is, as you can see the blank graph here, we are plotting n times the cell potential. And on the x-axis, we are writing the oxidation state. So all Frost diagrams have on the y-axis n. N is the number of electrons required for that oxidation state to reach the zero oxidation state. For example, if we have HNO3, the value of N will be 5 because you need to supply 5 electrons to go from nitrogen 5 plus to nitrogen 0. Similarly, if you have HNO2, the value of N will be 3 because you need 3 electrons to go from nitrogen 3 plus to nitrogen 0. Am I clear? Is that clear? So that's what the N value is. I have 2 people waiting on the calendar, so I'll just admit them now. So on the x-axis, we are plotting the oxidation state. Now, the potential here, E0, on the y-axis represents the redox potential for any oxidation state to 0. So for example, if I have HNO3, that E0 represents HNO3 to nitrogen gas. Whatever the potential is, that's what we are plotting on the y-axis. I hope that's clear to you, right? Now, we're going to show you some examples of Frost diagrams here. As you can see, this is a Frost diagram of the nitrogen in different oxidation states. The blue line here corresponds to the stability of nitrogen containing species in a base, and the red line here corresponds to the stability of the species in an acid medium. So if you look at this graph has a 0. Can you all see my pointer here on the screen?
Yes.
Thank you. So that's the nitrogen. See, the nitrogen corresponds to 0 right there. That is the elemental form, right? And you have on the red line all different species in an acid medium, and the blue line, you have the deprotonated species. For example, if I have HNO2 there, in a base, you cannot have protons, so you have only nitrite anions. So that's the reason why the blue line contains deprotonated forms and the red one contains the protonated forms. Okay, in any case, the nitrogen is still 0. Now, if you look at this plot very nicely, as you can see, N2O, NO, HNO2, N2O4, HNO3, they all go up. So here are the important points about this graph. Number 1, the most stable species, according to this graph, are the ones that are the lowest in the point. For example, NH4 plus is the most stable form of the nitrogen. That is, nitrogen 3 minus state is the most stable state because NH4 stays below nitrogen, as you can see. Okay. It doesn't mean that N2 will directly convert to NH4 plus. It doesn't talk about the kinetics because the cell potentials are a thermodynamic property. So we're only looking at the thermodynamics. We're not saying that N2 will instantaneously get converted to NH4 plus. Rather, we say that NH4 plus is more stable relative to N2. Now, if a species lies on the very top of the Frost diagram, that tells you that species is the most unstable one relative to the elemental form. So if you look at HNO3, which is on the top, that's the most unstable one because HNO3 will get converted to N2. That is the most stable state. Okay. So it now tells you different stabilities, N2O4, HNO2. So it tells you HNO2 is relatively more stable compared to HNO3, NO is relatively more stable compared to HNO2. So the lower the point in the Frost diagram, the more stable it is relative to the one that is above. Am I clear here, folks? That's a very useful information that it tells you. The second thing it tells you is, if you really look at this graph very carefully, I want you to pay attention for NO, HNO2, and N2O4, right? They're not exactly in a straight line. The HNO2 point is slightly left of the graph relative to NO and N2O4. Whenever you see that, it tells you that the midpoint, the HNO2, is not stable against disproportionation. In other words, it breaks down to N2O4 and NO. So if the graph, the point is on a concave that is below this curvature, it is unstable against disproportionation. If it is on the convex, on the other hand, if it is above the line, then it tells you it is the comproportionation that is stable. Okay, so here are the oxidation states that we have written down on the x-axis: -3 for NH4 plus, -2 plus N2H5, and NH2OH is -1. So these are all the different oxidation states that are possible for nitrogen, and it tells you the relative stabilities. Unlike the Latimer diagram, where you need to calculate different things and you just have to see disproportionation, comproportionation based on the right-hand side potential, left-hand side potential, you don't have to do all these things. You just look at the graph and look at the curvature on the point. So if it is concave, then it is unstable against disproportionation. If it is convex, then it is unstable against the comproportionation. Okay, so that is how the diagrams are constructed. And so here is the physical meaning of this. This N times E0 is a fragment of the Gibbs equation here that tells you that delta G equals negative NFE. So the N delta E0 is very similar to NE0, except, of course, we have the full redox potential rather than the change in the energies. And here N refers to the oxidation state, which is the number of electrons required for that oxidation state to reach 0. This is something that you have to keep in mind, that N is not an arbitrary number. It tells you how many electrons are required to convert that oxidation state to a neutral oxidation state or a 0. Okay, so this is the oxidation state, number of electrons required to reduce or oxidize a compound to its elemental form. So for example, in the case, it is N2 in this case. All right. So sometimes you need to oxidize, sometimes you need to reduce. For example, if you have the nitrogen in -3 oxidation state, you need to oxidize it by removing electrons to reach the neutral state. On the other hand, if it is in a positive oxidation state, you need to bring it down to 0 by adding electrons. So the N here refers to the total number of electrons. That's something that you have to keep in mind. So here is the plot that we use. That is basically free energy over the Faraday's constant, that is the Ne0 versus the oxidation state. So the position of nitrogen in this graph gives its stability relative to nitrogen. So this is the same figure repeated here in a smaller scale. Basically, it tells you which one is more stable. So by looking at this, of all the compounds nitrogen makes with oxygen, there are only 2 of them relatively more stable. One is nitrogen, the other one is NH4+. N2H5 is also relatively stable, but not as stable as the N2. Okay, so the remaining ones are very clear. And then you also know the strongest oxidizing agent is going to be HNO3. The one that is on the top of the graph is the one that is the strongest oxidizing agent. That means it has the strongest or the highest standard redox potential. That's what this graph is about. So that's what the graph now here tells you. The most stable oxidation state is the one that is the lowest in the graph. In the case of nitrogen, that was 0 or the NH4+, and the one that is on the top is the most oxidizing thing. So a number of things can be derived from a given compound. So for example, if I take this nitrogen here, NO, for example. So we can look at the point NO and draw a vertical onto the X and the Y axis. So it tells you the oxidation state on the x-axis, that is +2 in the case of NO, and the total potential here is about 3.3 or so, right? So once you know the potential and the number of electrons, that is the 2 electrons, you can take that potential, divide that by the number of electrons to get the redox potential. Similarly, if you have HNO3, the Ne value in volts is about 6.2, and the oxidation state of nitrogen is 5+. So if you want to know the redox potential, you just look at this graph and calculate in the following way. So HNO3 to nitrogen, it requires 5 electrons, right? So if you want to find the potential, on the y-axis, you have 6.2 volts. On the x-axis, you have 5. So 6.2 divided by 5 is 1.24. So you know the standard state potential very quickly just by looking at the Frost diagram. So that's the advantage of this. Similarly, if you have to find the redox potential of the NO to N2, we look at the Ne0 value, which is 3.4, and the oxidation state is 2+ here. So you need to add 2 electrons. So 3.4 divided by 2 will give you the potential 1.7. That 1.7, again, mind you, is the redox potential from NO to the neutral nitrogen. Similarly, the 1.24 you see in the HNO3 is the potential for the reaction in which the HNO3 gets converted to nitrogen. So this is how a Frost diagram helps us to evaluate various oxidation states. And if you look at this graph here, right? Let's say this is the lowest standard state potential, highest one right here. If you look at these 3 points, 1, 2, and 3, you can see this point is to the right of the line joining the points here and the top. So what does that tell you about the stability of this? Is it, does it disproportionate, or is it more stable so that these two oxidation states combine to give you this? In other words, is it comproportionation or disproportionation? Forget about the point on the left. I'm just talking about the 3 points here, 1, 2, and 3. If you look at this, right, this looks like a convex plot, right? So this point is on the right of the graph, right of the line joining the points 1 and 3. So clearly, this is more stable compared to points 1 and 3. So this is a comproportionation case. If this point were to stay to the left of the line joining it, then that species will not be stable against disproportionation. And another thing that you also want to know is the slope of this line tells you the standard state potential. That is the potential from point to point. So if I have 2 points on the Frost diagram, if I calculate the slope, that slope corresponds to the potential of the standard state redox potential. All right. So these are all the advantages. So in all advanced redox laboratories, people who work on redox chemistry, they find Frost diagrams to be extremely useful, and it gives you a snapshot, and you don't have to go through all the different numbers, look at all the values. The graph itself will tell you a much more easier way of understanding the relative stabilities of the species. All right. So here are some other stable species here. If you look at the peroxide, I want you to look at the red line here, which is the Frost diagram for the oxygen, hydrogen peroxide, and water. So what does it tell you about the relative stabilities? In acid medium, if I have oxygen, H2O2, and H2O, which one is more stable? These are the kind of questions you'll get in the exam. Given this graph,
H2O.
the H2O is the most stable. You are absolutely correct, right? The oxygen here is the most oxidizing thing here, because oxygen wants to get reduced to an oxide, and for that reason, oxygen is a good oxidizing agent. And what does it tell you about the relative stability of H2O2 relative to oxygen and H2O? Is H2O2 more stable than oxygen and H2O, or is it less stable compared to O2 and H2O? Does it, what did we talk about just before? So what I'm trying to do is Suppose if you were to draw a line directly from H2O to O2, where would that H2O2 point be on that line? Is it to the left or to the right of that line?
Left.
If it is left, what did I say?
Was
It's
left
not
stable?
right. It's unstable against disproportionation. So what it tells you is H2O2 will spontaneously undergo self-redox process, which is disproportionation, to give you oxygen and water. So a mixture of oxygen and water is more stable than peroxide. You see how quickly we can see this in the graph. Does that make sense, folks? Yeah. So let's take one or two more examples. I think this is the last one, I believe. Yes, this is the last one. Kind of summarizes the frost diagrams. Any questions on frost diagrams? Anything that's not clear? I will upload this part of the presentation as a separate file into the Canvas. And of course, all the presentation we have made just now also will be available as a link. Okay. If there are no questions, then we need to move on to the next topic, which is what we call catalysis. Right? Can you all see the board here, folks?
I can see it.
Gurveer, can you see it?
Yeah,
No
I can see
flickering.
it.
It's a little better than before.
Yeah, it's good.
Okay, great. Okay. So I'm sure most of you must have heard the word catalyst, right? In your Chem 2 classes or other classes. What is a catalyst? Can anyone help me with the definition of a catalyst?
It's
When do
I think it's a
we-
protein that speeds up the reaction
Hmm?
by lowering the activation energy, I think. Maybe.
What is the other attribute of a catalyst?
It's not used up in the reaction.
Thank you, Mike. That's very important. That's not consumed, right? So a catalyst speeds up a chemical process without getting consumed, right? And as Gurveer said, the way this does is basically it reduces the activation energy barrier for the reactants to get converted to products by creating alternate different pathways. So for example, if I have the energy and reaction coordinate here, so for an uncatalyzed process, if your reactants are here, and let's say we have products here, so the reactants have to go through a hill, come back, and the activation energy is defined as the highest point of energy relative to the reactants. That's your delta E. And there are ways of calculating this. Most of you know this, right? You find the rate of the reaction as a function of temperature, and you plot the log of the rate of reaction as a function of inverse of temperature, and the slope will tell you the activation energy. Most of the reactions don't undergo this because of high activation energies. That is the roadblock for a chemical reaction to happen. So what a catalyst does is it changes the path of a process. Instead of going through one step, it might go through multiple steps. All of them give you a lower activation energy. Now, again, in the presence of a catalyst, if you have multiple hills and valleys, Again, the highest one refers to the activation energy here. That definitely is smaller than the activation energy you have for the uncatalyzed reaction. Uncatalyzed reactions have very high activation energies. So this is how a catalyst changes the path of a reaction. It provides an alternate route where the energy required for the reaction to proceed from reactant to products is lowered significantly. That's exactly what a catalyst is. Would you all agree with me with this? I mean, is that you all know about this, right? Any questions on the definition of a catalyst? Does a catalyst change the delta H of a reaction?
No, I don't think so.
Does it change the delta S? Does it change the free energy? Does a catalyst catalyze a thermodynamically not favorable reaction to a thermodynamically favorable reaction? Let's say if a reaction has a delta G greater than 0, is that spontaneous or non-spontaneous?
Non-spontaneous.
So if a reaction has a delta G positive, it's non-spontaneous. Can I make it spontaneous by adding a catalyst?
No.
Yes or no? Sorry, if, I didn't hear if somebody answered this. My question is, does a catalyst turn a non-spontaneous reaction to a spontaneous process? What's your gut feeling? Yes or no?
I'm gonna say no.
God bless you. You are absolutely correct. A catalyst will never change the thermodynamics of a process. If a reaction is not favored thermodynamically, a catalyst won't change much. What it can do is, if a reaction is favored thermodynamically, it will only speed it up. In other words, the rate at which a reaction reaches equilibrium is enhanced in the presence of a catalyst. It will not change the equilibrium constant value because the equilibrium constant is related to the delta G. So it doesn't change the K value, which is the equilibrium constant. What it basically does is it changes the time it requires to attain the equilibrium, how fast a reaction reaches the equilibrium, not the equilibrium constant. So these are some of the things that you have to keep in mind. These are all the basics of a catalyst. That now brings us to the point of what exactly inorganic chemistry got to do with the catalysis. Well, about 95% of the chemical processes, industrial chemical processes, require a catalyst. Without a catalyst, there is no industry. So catalysis plays a huge role in the production of fine chemicals. Now, what makes a catalyst a good catalyst? You may have many catalysts, right? So how do people choose a catalyst? There are 4 important parameters that will help you with the catalysis. So let me get to this. Let me take this off. These are all the industrially important processes. Number 1 is selectivity. a catalyst, for it to be a good catalyst, it must be selective towards the formation of a particular product. Let's say if I have a reaction between ethylene and oxygen. What kind of products can you expect from this process, folks? What's the most thermodynamically favored process here? If I take ethylene, C2H4, and heat it in oxygen, what do you get?
Shouldn't you get carbon dioxide and water?
You're absolutely correct. That's what the combustion reactions are, right? All hydrocarbons, when you burn them in oxygen, you get carbon dioxide and water. But in the presence of a catalyst, you can selectively do an oxidation where you can get C2H4O, ethylene oxide. So if you don't use a catalyst, and if you do this reaction, you get exclusively carbon dioxide and water. On the other hand, if you want to use a catalyst, in this case, it's silver oxide. If you use silver, slightly oxidized silver, then it will give you the epoxide. So this is the epoxidation process. Without the catalyst, of course, you're going to get carbon dioxide and water. So selectivity is a very important criteria for catalyst. That is number one. Number two is long life. You don't call a catalyst if it works for 10 minutes and dies. Even if it is world's best catalyst, people will not buy it because you want a catalyst that can perform for months together. A lot of times people discover a catalyst and then say, I have a superior catalyst, but it works only for 10 minutes. No good. Industry will not take it. So for a good catalyst, you need to have a long life, both in the reactor as well as outside the reactor. So you should be able to store it for a longer period of time without affecting its catalytic efficiency. And once you put it in the reactor, it must run continuously. For example, if you are in a petroleum industry, we use a lot of catalysts like zeolites. We'll talk about that later on. But if the zeolite works only for a month, and if the technician has to change all the zeolite and put a new one every month, that's not profitable for the industry. So you need to design a catalyst that will stay and function for a longer period of time. Even if you have a superior catalyst, it can give you, let's say if you have a catalyst that works 10% better than what you have already, but it requires a change every 15 days, it's not going to make it to the industry. You might be able to publish a paper in Science or Nature, but it will not cut to the industry. The requirements, industrial requirements are entirely different compared to the academic requirements. So these are all important parameters when you're designing a catalyst. The third important aspect is it should be fast enough. What do you mean by fast enough? So an uncatalyzed process might take, let's say, a year, but in the presence of a catalyst, it should happen in about 10 minutes. That's what we're talking about. It should be fast enough so that you'll see visibly a change in the reaction in the presence of a catalyst. Number 4 is the reaction should be thermodynamically favored. If a reaction has unfavorable thermodynamic parameters, such as, positive delta G, a catalyst is not much of help for you. So you need to choose your reactions properly, right? So how do people rate the performance of a catalyst? So here is how they do. We use a term called turnover number or turnover frequency. Like TOF, not time of flight. Time of flight is in analytical chemistry, is a chromatography point. This one is turnover frequency. So let me define what a turnover frequency is. Let's say if I have a reaction A giving B. Okay. The rate of the reaction or the velocity of this process is changing the concentration of the product divided by time. Right? That's the speed of a reaction, rate of a reaction. So if the rate of reaction is V, then the turnover frequency is defined as the rate of the reaction divided by the concentration of the catalyst. So Q is the concentration of the catalyst. So higher the turnover frequency, the better the catalytic efficiency is. So if you're designing a catalyst, you want to have V higher, the numerator must be high and the denominator must be small. So the concentration of the catalyst must be smaller and the rate of the reaction should be high. So whenever you have 10 or 15 catalysts, and if you want to quickly screen them, people use the turnover frequency and see what is the amount of catalyst required to attain a particular given speed. Higher the concentration of the catalyst, it's not generally, not taken favorably by the industry. They want to have very small amount of catalyst and very high rate of conversion. So that is the industrial parameters. Okay. The next thing is catalysis, in my personal opinion, is more of an art than science, but in general, catalysis can be divided into 3 types. One is homogeneous catalysis. Second one is heterogeneous catalysis. And the third one, enzymatic. Enzymatic catalysis is studied mostly in biochemistry courses. So in inorganic chemistry, we'll try to work mostly on homogeneous catalysis and heterogeneous catalysis. So again, that begs for the definition. What is a homogeneous catalyst? A homogeneous catalysis is when the reactant and the catalyst are in the same phase. For example, if you have a liquid reactant and the catalyst is also a liquid, when you mix 2 of them, that is a homogeneous catalyst. Or if your catalyst and the reactant are gases, if both are gases, that is again a homogeneous catalysis. On the other hand, in heterogeneous catalysis, the reactant and the catalyst are not in the same phase. For example, you can have a solid catalyst onto which you pass a gas, a gaseous reactant, and you perform catalysis there. As you can see, the catalyst is solid, the reactant is a gas, or it could be a liquid. As long as they're not in the same phase, we say that is heterogeneous catalysis. In industry, both homogeneous catalysis and heterogeneous catalysis are applied routinely, although heterogeneous catalysis has some advantages because you pass a gas or a liquid through a solid, on the other side, you collect your product. So it's very easy to perform. On the other hand, homogeneous catalysis, when you convert the reactant to the products, you need to do a separation of the product from the catalyst. It's an additional step you need to do. But sometimes it is more economical to get it done this way. So in industry, both homogeneous and heterogeneous catalysts are used. Recently, in the last 5 years, there is a drive to convert most of the homogeneously catalyzed processes into what we call semi-heterogeneous processes because of ease of operations. But still, there are some processes, we have no choice. We have no other alternatives. We have to use homogeneous catalysis. So in industry, both are used. So we need to know exactly how does the homogeneous catalyst work versus how does a heterogeneous catalyst work. But before I continue with that definitions, are there any questions so far? Anything that's not clear? Okay. All right, so let's now take some real life examples. So I spent a lot of time collecting the real industrial processes that are currently being used as an example of the homogeneous and heterogeneous catalysis. So let's talk about homogeneous catalysis to begin with and move into heterogeneous catalysis. I'll be very careful not to bore you with a lot of details because I'm a little passionate about this area. I did my PhD in heterogeneous catalysis. So I try to stay away from as details because sometimes you get carried away on your research topic of your interest, right? So we'll try to give equal preference to homogeneous, heterogeneous, and some real life examples. Okay, let's continue. In homogeneous catalysis, we have what we call a catalyst cycle. Most of the homogeneously catalyzed reactions involve coordination complexes. Okay, majority of them are coordination complexes. We will start this process with a Nobel Prize winning homogeneous catalyst process, right? So here is how it started. If we have triphenylphosphine, this is sometimes written as PPH3, that's a phosphorus connected to 3 phenyl rings. So triphenylphosphine. We call this a ligand, okay? Because I will not be able to write the entire formula all the time in the coordination complex. I will call this simply a ligand that will be used in real life catalysis. All right, so ruthenium complexes so this is the starting complex for the hydrogenation of olefins. Hydrogenation of olefins without the catalyst require extremely high temperatures and very poor yields. But in the presence of a catalyst, you can do hydrogenation of olefins at relatively low temperatures. I'm talking about 50 degrees, 40 degrees Celsius, and at relatively moderate pressures like 1 atmosphere. And the catalyst that was discovered by Jack Halpern and Wilkinson, both of them got Nobel Prize for the discovery of this catalyst. I'll explain to you how this catalyst works in terms of converting an unsaturated olefin into a saturated olefin. All right, so this is chloro tristriphenyl ruthenium. What's the oxidation state of ruthenium in this complex? Remember, we talked about all these coordination complexes. There's a reason why we talked about this. Because there's a huge application of these complexes in industry.
+1.
You're absolutely correct. That's +1 because we have chloride. Chloro is negative. These three are neutral ligands. Triphenylphosphine is a neutral ligand. So ruthenium is a 1+ compound here. Okay. What kind of a geometry you think this complex will have? Is it tetrahedral or square planar? Ruthenium 1+ complexes, right? It's D8 complexes.
I think it's going to be tetrahedral.
Is it? What type of complexes do have tetrahedral things? Remember lead, right? Iodides, main group metals generally have tetrahedral complexes. Some zinc complexes are tetrahedral, but majority of the transition metal complexes, nickel, ruthenium, rhodium, palladium, platinum, these always form square planar complexes. So this one is a square planar complex, just the way it is written. All right? Okay. So let's see how this cycle happens. I want you to pay attention to all the steps here. Now that I have introduced what a ligand is, what chlorine is, and all that stuff, we're going to write a cycle for the first thing that happens here is this is the ruthenium, 3 triphenylphosphines, and chlorine. Can you all see that board there? If you can see, let me know. The first thing that we do is we take a solvent, and one of the solvent gets exchanged with the ligands and forms ruthenium solvent, 2 ligands, and a chlorine. This is the catalyst. Okay, so we're now getting into the cycle. Please pay attention here. This is the ruthenium. There's a solvent molecule here. The solvent could be water. It could be, chloroform. And we have triphenylphosphine here, and a triphenylphosphine here, and a chlorine here. This is a square planar complex. Now, square planar complexes have excellent lability. Remember, we talked about labile complexes. The reason for that is in a square planar complex, the ligands can approach, the new ligands can approach either from the top or from the bottom. Both are empty. So these are what we call coordinatively unsaturated complexes. A square planar complex, and if you compare that with an octahedral complex, right? An octahedral complex has 6 ligands, square planar is only 4. So you can add ligands on the top and the bottom. Okay, so it's what happens. The reaction we're trying to do is C2H4 plus H2 giving C2H6. That is the reaction we're trying to catalyze using the ruthenium complex. This is an olefin, and we have hydrogenation of olefins to give you the alkanes. It's a C2H6. All right. The first step here is the hydrogen adds onto this complex in a dissociative fashion and forms, very interestingly, a complex like this: ruthenium, hydrogen, hydrogen, solvent, and ligand, and chlorine here, and ligand. That's an octahedral complex. The hydrogen now splits and takes up the apical positions of this octahedron. And the next step, what happens is we add C2H4 and remove the solvent. So we put conventional like this: plus C2H4 minus solvent means the alkane here attacks the solvent and the solvent is removed. So what you get here is RU, and then we have CH2 double bond CH2, and then we have the hydrogen here, hydrogen there, and the two ligands here, and the chlorine. What did we do here? We have substituted one of the ligands with C2H4. Remember, we talked about the lability of the complexes. If a complex is not labile, if it is inert, it's not a good catalyst. So all catalysts are, one of the important requirements is they must be labile. You should be able to exchange the ligands freely. So that's what exactly is happening in this case. So the pi bond here in the ethylene, those two electrons bind with the ruthenium to form this complex. The next step, what happens is the solvent that is left there now tries to attack this complex, and as a result, one of the hydrogens there gets migrated here. So the solvent goes where the hydrogen was before, and the hydrogen then gets migrated to the alkene to give you a complex like this: RU, H, SOL, the solvent again molecule, and this time we have CH3, CH2, we have another hydrogen here, and then we have the ligands, the triphenylphosphine, and also the chlorine ligand. Okay. Now this one, you have a proton here and the CH3, CH2 fragment. This will leave as C2H6. As these two groups leave, you come back to this catalyst. So this is almost like a cycle. So this is one full cycle of the hydrogenation of unsaturated olefins. Am I making sense here, folks? So you start with a complex. So this is what we call, it's not exactly a catalyst. This is called a catalyst precursor. The chlorine, ruthenium, trisphenyl chloral complex, and you add a solvent and you make a complex. That is the actual catalyst. And this catalyst undergoes hydrogenation. So two hydrogen atoms add, splits the hydrogen molecule into two hydrogen atoms, and each hydrogen acts like a hydroid ligand, and you have the hydroid ligands, and the hydroid ligands, they get attracted with the C2H4 at the solvent site. The solvent leaves temporarily and gives place for the ethylene molecule to get binded to the ruthenium. And the next step, the solvent again comes back and attacks this proton. This proton now gets transferred. This is what we call a migration process. So the ligands migrate from one place to the other place. When that migration happens, you get CH3, CH2. And the final step, this proton and the CH3, CH2 ligands combine here, go back and form the complex. So this mechanism won the Nobel Prize. So the question then is, what is the catalyst doing here? To appreciate the beauty of this process, we need to first understand the physical state of the reactants. Both are gases, right? Yeah. If you don't have a catalyst, what does your PChem tell you in terms of the possibility of having two of these gas molecules having the right orientation to come and attach itself? You need to have the pi bond lined up with your HH bond, right? For the addition to happen. What are the chances there? In a gas phase at high temperatures, these molecules are undergoing a lot of rotation, vibrations, right? Tumbling. When that happens, you don't have any orientation that will give you the hydrogen and the C2H4 to come to the right orientation. What did the catalyst do? It grabbed the hydrogen and it grabbed the C2H4 and it anchored them on the complex. Once they are the proximity, now the catalyst will allow the reaction to happen without having to worry about entropic conditions here. In other words, it made the reaction more facile just by bringing them together and providing in the proximity. For example, the hydrogen now is in very close proximity to the ethylene molecule, and the reaction can happen now. And this one, the turnover frequency is about, I don't know, I think it's about 20 or 30,000 reactions per second. So this process, in 1 second, it converts about 20,000 molecules per each ruthenium complex. So if you have millions of ruthenium ion molecules, ruthenium complexes molecules, and with that turnover frequency, the reaction happens spontaneously and instantaneously and with very high specificity. Remember, selectivity is a very important criteria for a catalyst. So majority of the homogeneously catalyzed processes that we're going to discuss will look very similar to this. There is always a cycle. You start with a catalyst precursor and you go through this. Now, some of you may ask me, how the hell do we know that this is how the reaction goes? In fact, this was not just a speculation. That's where Jack Halpern and Wilkinson did enormous amount of work, do them almost 15, 20 years to figure out this process. It looks very simple now, but when they started, they had no idea how this reaction was going on. They were able to isolate some of these complexes, characterize them, and they know that they are the intermediates here. So they now had the different pieces of the puzzle, and they put them together and came back with the cycle. So majority of the homogeneously catalyzed processes, that is the advantage. You have a reaction mechanism either from IR or either from crystallography or from NMR. You should be able to look at the different intermediates and propose a reasonable path for the homogeneously catalyzed processes. Is that clear to all of you? Okay. I just gave you an outlet, but then I'm going to do some anatomy of this. How many different steps are involved? What exactly is happening when the hydrogen is attached here? Is it getting oxidized or reduced? What happens when the alkane leaves? Is it a redox elimination or oxidative addition? So what are the steps involved in all these processes? So by looking at a variety of homogeneously catalyzed processes, they figured out majority of the homogeneously catalyzed processes have approximately 5 different steps. So let me now start with the different types of steps involved in the catalytically induced processes. Number one, the first step in all homogeneously catalyzed processes is what we call number one is ligand coordination. Or and dissociation. So the way we contemplate this is, if I have a square planar complex with a metal and 4 ligands, when you add a new ligand, you get an intermediate where you have the ligand, the new ligand gets associated with the existing complex. This is commonly seen in most of the homogeneously catalyzed processes. The next step, the next one is what we call insertion. And the opposite of insertion, or the reverse of this insertion, is what we call elimination. Now, the way we look at this is, let's say I have a complex in which a metal is bound to carbonyl, right? And then we have a ligand here, and we have another ligand here, ligand. Now, an insertion happens when one of the ligands gets in between the metal ligand bonds, and you get MCOL and L complexes. That is an insertion process where one ligand gets inserted between a metal and a different ligand. We're going to give you tons of examples of all this. What we want you to understand is whenever you see a process, you should be able to identify what that process is. Is it insertion? Is it elimination? So on and so forth, okay? Good. The third one is what we call nucleophilic attack on ligands. Nucleophilic attack on ligands. So for example, if you have a palladium complex with 3 ligands, and let's say it is attached to an ethylene palladium complex here. Now you can have water that is outside the coordination sphere. This can attack the double bond on the ligand and give you L3PD. I'm not putting the ligands here, it could be triphenylphosphine ligands. I'm just writing as L3PD. And then we have CHH and CHHOH. So what did it do? It just basically created an alcohol bond right there. The water attacking the ligand that is attached to the complex here. Sometimes this is a process. The fourth one is oxidation and reduction. In some catalytic processes, the metals undergo oxidation or reduction. In other words, the electrons of the metal shuttle between oxidized state to reduced state. In the process, they will do catalysis. We'll see some examples of that as well. And the last one is oxidative addition. And opposite of oxidative addition is what we call reductive elimination. Remember the previous example where we saw the square planar complex ruthenium, the triphenyl phosphine solvent process. When we added hydrogen to it, this hydrogen added and made an octahedral complex. So what happens to the oxidation state of ruthenium now, folks? Before the addition of the complex, we said ruthenium is in +1 oxidation state. What happens to the oxidation state when you add two hydride ligands? Hydride is H minus, right? So what happened here? The oxidation state from +1 now goes to +3. So there is an oxidative addition. In other words, there is an addition of hydride ligands here, and that is followed up by the oxidation of ruthenium from +1 to +3. In general, most of the additions are oxidative additions. Now, if you look at the reverse of this process, that is what we call reductive elimination. Let's say if the hydrogen goes and the ruthenium comes back to +1 state, this is an equilibrium, right? So the forward reaction is oxidative addition, and the reverse of this reaction is reductive elimination. So elimination followed by a reduction in the oxidation state of the ruthenium. Am I clear here, folks? Any questions so far? Anything that's not clear? We're going to give you lots and lots of examples. In fact, each cycle takes about 15-20 minutes to start to finish. So I'm going to give you most industrially relevant processes. And you see, this is how much of inorganic chemistry goes on here. Transition metal complexes, oxidation, reduction. And we're talking about ligand association, dissociation, the lability of the complexes, and how people come, the choice. The majority of the problems, ruthenium is very expensive metal. Palladium is expensive. Did you guys note last week, palladium exceeded the cost of platinum or gold? It is the most precious metal now. So anytime you have an industrial process that has palladium catalyst, the industry wants to see if you can discard an alternate catalyst without having palladium. Because cost is a big factor. And there's not much of palladium on this planet to go around. So these are all some of the challenges. That's what this inorganic chemistry is all about, okay? So I think for now, we have not much time to start process. We will definitely do that next week. Next Tuesday, we will come back and look at Monsanto process of acetic acid. We look into a variety of other industrially important homogeneously catalyzed processes. Okay, folks? So see you all next Tuesday, same time.
Bye,
Thank you for
Charlie.